Hi there, grade 12. We're still going along with our study of the interference patterns of water waves. And in this one, we're going to look at a secondary equation. So we've already gone through one equation involving the path difference, and we're going to see that equation break down in the situations where our points are really far away from the sources, so we can't get a good value for the path difference, or if our wavelength is just really small. So what we're going to be seeing are some patterns where that destructive interference happens when your path difference is some odd number multiple of half a wavelength. So if your wavelength is really tiny, half a wavelength isn't going to be something that you can necessarily pick up with a measuring tool like a ruler. So we have a second equation and then a third that we can use in some of those cases. This is the second equation right here on the screen. And we've got sine of an angle. This angle is really hard to define in words, so we're going to describe it in our diagram. N is still the nodal line that our random point we pick is on. Lambda is still the wavelength, and now we have D. D is the separation between your two sources. So that's what we're looking at here. And this is something else that we're going to just measure with our ruler. So, steps. The first step that we're going to take in applying this equation is the same as the first step in the previous situation, which was to pick a point. And you're going to pick a point on any one of your nodal lines. So maybe you do the first one, maybe you want to do the second one. Let's get a little different here. Let's pick a point on our second nodal line, just for fun. So this is that first nodal line, that's that first fuzzy area. Here's our second nodal line, it's that second fuzzy area. So here's my point, and this time we're going to use n equals 2. Now this is where our diagrams are going to get a little bit funny. So the second step here is to get really creative with our diagram and draw a triangle. Now I know by grade 12, drawing a triangle probably doesn't sound like a really interesting step, but it's a very specific triangle. So to use equation 1, we would connect that point to our source, measure the length of each of these lines. In this case, this would be P2S1 and P2S2. These are on the second nodal line. But remember, we're looking at what if we couldn't actually make that physical measurement. So what we would have here is a very small triangle, which involves the distance between our two sources. We'll call that D. Remember, we were calling that D before. And then we're going to draw in a triangle such that it creates a right angle with our longer line. So this little angle here is a right angle. This D value becomes the hypotenuse of that little teeny tiny right triangle. And then this angle here, that becomes our theta n value. In this case, n is 2, so that becomes theta 2. That's what that angle is there. We're just going to zoom in on that a little bit, see if we can't see it a little bit better. So we've made a teeny little right triangle where D becomes the hypotenuse, and then the angle we're after, theta n, is just between that hypotenuse and that little imaginary line we drew in. Okay? So their third step is going to be to make some actual measurements. And the things that we're going to measure are going to actually be this D value and this angle. So let's go ahead and make some measurements. I'm just going to write in that step. So that we can go ahead and do that. So we're going to measure D, and that will be with our ruler. and we're also going to measure theta 2, and that would be with a protractor. Now, if you don't have a protractor, because I know a lot of you might not have those at home, you might have to get a little bit creative with your primary trigonometric ratios. So I'm really hopeful that you all have a ruler, or maybe you can print one off of the internet. I'm going to take my ruler here and figure out what our D value is. So we're measuring the distance between the centers of our two sources. And I've got about, let's say, 1.85 centimeters. And we're going to measure our angle. I've lined up the center with that line that has D on it. It reaches 0 along the outside numbers, so I'm using those outside numbers to make my measurements. And if I look along here, it looks like it's about, tiny. Can I use this one to help me? About 26.5 degrees. So we're going to get a pretty lousy answer here because that's a really big angle. And these equations tend to work best when our angles are really tiny. But the tinier they are, the harder they are to measure. It's a little bit of a conundrum there. Now our next step is going to be to substitute all of these values and solve. And I do not hold your breath for a good answer on this one. But the important thing is that we're coming out of this with an understanding of what these values are. Already there. A few substitution faux pas. All right. And we should be substituting 2 for our nodal line. And then for our separation of sources, we have 1.85 centimeters. Now, this is just going to give us a dimensionless value. This is a counting number. So again, because this is the only thing with units, centimeters, our wavelength is going to be given to us in centimeters. And if we solve all of this, we're going to get about, make sure your calculator is in degree mode here. Oh, not as bad as I was expecting. Go us. So I got about 0.55 centimeters. Actually went pretty well. I'm going to do one more little video clip where we go through equation 3 and how we can apply that, because this situation is going to fall apart a little bit when our angle is too small to measure. So let's see what that would look like.